Okay, one important message to learn in this chapter is that integrals like this, where the upper limit is a variable, define functions. You have One has a strong tendency to, once you see an integral like this, to try to compute what is the integral, the value of the integral, the expression, right? But sometimes it's impossible, and this is the case of this function, right? Anyway, even if you are unable to express this as an expression containing elementary functions, right, which will most of the time be the case, still, this is a valid function and it has any other property that other functions defined in different ways have. So in particular, if you have this function here, you can ask yourself what are the absolute maxima, minima in a given interval or whatever, right? Or where is this function growing, decreasing, even try to plot this function. So anything that you can do with functions, you can do it with integrals, functions defined through integrals, even if you are not able to express this integral in any other simple way, right? So that is exactly what we're going to do here. This expression is impossible to express in terms of elementary functions, right? So we have to deal with this function as it is, okay? Right. So what you do when you want to calculate what is the maximum, the minimum, or etc. of a function? Well, we have to first make sure that the function is differentiable, and second, try to solve the equation f prime equal to 0, right? And this determines what are the local maxima, and then we have to compare with the extremes of the interval and see if you find the absolute maxima and minima. All right. Well, of course, this is a continuous function, okay? So if you integrate a continuous function like this, what you get is a differentiable function, right? So this function is differentiable everywhere. So we only have to worry about what the solutions of this equation, okay? Okay, so let's take the derivative of this, right? The derivative of this is equal to, well, we apply Leibniz rule, right? We have here a function, so we substitute this by the function, so it's x minus 1 square minus e minus 2 x minus 1, and then you have to multiply this by the derivative of this, which is just 1, right? Okay, so that is the derivative of the function, and we want this to be 0. As a matter of fact, we want to see where this is positive, negative, or whatever. So we want to see what the sign of this is. So let's try to see when is this positive, for instance, right? So this is going to be positive if e minus x minus 1 square is larger than e minus 2 x minus 1, right? Okay, the exponentials are increasing functions, so if we want to see if this one is larger than this one, well, all we have to see is whether this exponent is larger than this exponent here. So we want to make sure if this, or when, is this larger than this here. Okay. Multiply by minus 1, or actually it doesn't, we don't have to. We just put this on the right side, and we have x minus 1 square minus 2x minus 1, and that is equal, and that has to be negative, right? So this inequality is equal to that if we put this here. Okay, we factor out x minus 1, so we get x minus 1 times x minus 1 minus 2, negative, which means that x minus 1 times x minus 3 has to be negative. And for that, x has to be between 1 and 3. Okay, so this derivative is increasing, this derivative is positive, and therefore the function is increasing, all right, if x is within this interval, between 1 and 3, right? Okay, now if we change the inequality here, then we change the inequality here, also here, also here, here, and here, and we have the opposite, which means that if x is larger than, well, f prime is negative is if x is larger than 3, right? Larger than 3. Smaller than 1, we don't care about that, because for x smaller than 1, we are outside the interval of interest here. Okay, so the function is decreasing beyond 3. So now we know that at the point x equal to 3, the function increases then decreases. So there is a local maximum. This is a local maximum. All right, but not only that. At the point 1, if we substitute here 1, this is 1, this is 1, so this is 0. So f prime at 1 is equal to 0, which means that x equal to 1 is a local minimum. Local minimum, right? Okay, we didn't find this because we just focused on this interval here, but if you don't focus on that, for x smaller than 1, you also have a decreasing function. So it's decreasing for x smaller than 1 and increasing for x larger than 1. So at 1 has a local minimum, right? Okay, so let's try to calculate what are the values of the function there, right? So we have f of 1, that is easy because it's the integral from 0 to 0, this is 0. And then we have f of 3, which is, well, whatever is the integral from 0 to 2 of this function, which is something that it cannot compute. We cannot compute except numerically. But anyway, this is going to be positive, right? This is a positive function because this argument here is positive in this interval here, right? Between 0 and 3. Okay, so anyway, what we have is a function, right? It's a function, okay, that is 0 here, then increases up to this point 3. Well, actually it's not at this point, not at 0. It's 0 at 1. So this is x is equal to 1 here. So at 1 the function is 0, so it increases, right, up to a point where is the value, the function reaches a maximum and then decreases, and it never increases again. So this is not only a local maximum, it's an absolute maximum. Okay, so the absolute maximum is found at x equal to 3. This is absolute, right? Okay, but about the local minimum, everything depends on the limit of this function when x goes to infinity. Because if this function goes to a limit which is 0 or above 0, then we know that 0 is going to be the absolute maximum because the function reaches the value 0. But if this limit is negative or even minus infinity, then there is no absolute maximum. This is just a local minimum. By the way, the form of this function cannot be like this. It has to be like this, right? Because the derivative, we know that the derivative here has to be 0. So it's got this form. All right, so everything depends on what is this limit here. But then we have to use a hint that we have here, which is the limit of this function is equal to, the function defined by this integral is equal to square root pi divided by 2. Well, this is something, I'm giving this to you as a hint, but this is something that you will be able to derive yourself in calculus 2, right? So keep this in mind. If you recall it, you will be proven why this limit here is the square root pi divided by 2. It's not very difficult to prove that, but you need to introduce several variables for that. Anyway, let's try to calculate what this limit is. So we need the limit of the function f when x goes to infinity, and we have two pieces. The first piece is the integral from 0 to x minus 1, x to infinity, and here we have the exponential of minus t squared dt, right? And then we have to subtract the limit when x goes to infinity of the integral from 0 to x minus 1 e minus t dt. All right, or minus 2t, sorry, minus 2t dt. Okay. To calculate this one is where we need this limit here. But it doesn't matter if you have x here or x minus 1, because when x goes to infinity, this goes to infinity. Whether it is x or x minus 1, doesn't matter. So the limit of that is square root pi divided by 2. So this limit here is square root pi divided by 2. Okay, so that's the first bit. Now for the second bit, this is an integral that we can calculate, right? The primitive of this is just, so this integral here, the primitive of this exponential is minus 1/2 e minus 2t, right? And we have to evaluate this in 0 and x minus 1, okay? Which is minus 1/2 x minus 2x minus 1 minus, with this minus is a plus, 1/2 of 1. Okay, so this is the value of the function. And if we take the limit when x goes to infinity, the limit of this is 0. Okay, the exponential decreases, so this is 0, and this is 1/2. So we have to subtract here 1/2. All right. So we have here a limit which is square root pi minus 1 divided by 2. But the square root pi is larger than 1, right? Because pi is 3 point something, and the square root of pi is like 1.7 or 8 or something like that. So it's larger than 1, definitely larger than 1. So this number is positive. So as I said, the limit here, the function approaches a value, but this value is a positive value. So it behaves roughly like that, okay, when x goes to infinity. So then the value it takes here is the smallest possible the value takes in the interval 1 to infinity. So 1 is the absolute minimum. And that's it, right? You see how to analyze this function. We have made use of the same kind of things that we use to analyze any other function. And in particular, we have helped ourselves with the plotting of the function, or the sketch of what the function looks like. We can't determine certain quantitative properties of this function. For instance, we cannot determine this value, the value it takes at x equal to 3, because it's, as I said, it's this complicated integral that you can only evaluate numerically. But we don't care, as long as this is a positive number, right? Because this is enough information to know that this is the absolute maximum. And for the absolute minimum, we only need this limit, which we are able to calculate given this hint here, which, as I said, is something that you will be able to prove in calculus 2. Okay?